Today, we delve into the world of quarks, the most fundamental particles known to mankind. Quarks are the elusive yet essential pieces that make up our universe, so tiny that even the most powerful microscopes can't catch a glimpse of them. Yet, despite their minuscule size, they play a monumental role in the grand scheme of the cosmos. Quarks are the elementary particles that nestle within the heart of an atom. They're like the invisible threads weaving the fabric of reality. They're far more minuscule than the protons and neutrons we learned about in school. Those protons and neutrons are made up of these infinitesimal quarks. But quarks aren't just small, they're also mysterious, each one carrying a unique set of properties that distinguish one from the other. As we journey further into the subatomic realm, we discover that quarks are even more intriguing and complex than we might first imagine. In the quark universe, variety is the spice of life. Scientists have identified 6 different types or flavors of these particles. Let's start with the lightweights, the up and down quarks. These are the most common quarks, forming the protons and neutrons that make up the nucleus of an atom. The up quark carries a charge of positive 2/3, while the down quark carries a charge of negative 1/3. And their spins? Well, they can be either up or down, contributing to their dynamic interactions. Now let's move on to the other 4 flavors: charm, strange, top, and bottom. These quarks are the heavyweights of the quark world and are only produced in high-energy particle collisions, like those in particle accelerators. The charm and top quarks carry a charge of positive 2/3, while the strange and bottom quarks carry a charge of negative 1/3. They have higher masses and different spins compared to the up and down quarks, making them a little more elusive in nature. But what truly makes quarks stand out is their color charge. Now don't get misled by the term. It has nothing to do with actual colors. It's just a quirky way physicists describe the strong force that binds quarks together. Each quark carries one of 3 color charges: red, green, or blue. And here's the fun part. They constantly swap these colors by exchanging particles called gluons. It's a never-ending game of color tag at a subatomic level. And let's not forget about the fractional electric charge. Unlike other particles that carry a whole number charge, quarks break the rule. Whether it's positive 2/3 for the up, charm, and top quarks, or negative 1/3 for the down, strange, and bottom quarks, they all carry a fractional electric charge. Though each type of quark is unique, they all share an intriguing property. They carry a fractional electric charge, a feature exclusive to quarks. Quarks do not live in isolation. They interact with each other through 2 primary forces: the strong nuclear force and the weak nuclear force. Now imagine the strong nuclear force as an invisible, unbreakable bond. It's the strongest force in nature, and it's what keeps quarks glued together. Speaking of glue, meet the gluons. These little guys are the mediators of the strong force, carrying the color charge between quarks and holding them together to form protons and neutrons. Inside the nucleus, the proton and neutrons are mainly made up of up and down quarks, which are 2 and 1 pair. A proton is 2 up and 1 down quarks, and the neutron is 2 down and 1 up quarks. They are joined by gluons in a Y shape. Try to separate them by putting energy. There will be no restoring or opposing force to counteract your force, but after a limit, when they are about to get separated, the energy you were putting in will form a new quarks-antiquark pair. On the other hand, we have the weak nuclear force, which is, well, weaker, but don't let its name fool you. This force is crucial in certain types of radioactive decay, making it an essential player in the world of subatomic particles. And who mediates this force? Enter W and Z boson, the unsung heroes of the weak force. Through these forces, quarks influence each other and the world around us, despite their minuscule size. The strong force is one of the 4 fundamental forces of nature, responsible for holding the nucleus of an atom together. It is the strongest of all the fundamental forces, and its strength is due to the interaction between up and down quarks, which are the building blocks of protons and neutrons. Up and down quarks are held together by a type of force called the strong nuclear force, which is mediated by particles called gluons. Gluons are constantly being exchanged between the quarks, creating a sort of glue that holds them together. The strong nuclear force is a result of the fact that up and down quarks have what is known as color charge. This is not the same as the color we see with our eyes, but rather a property that exists in the world of particle physics. Quarks can have one of three color charges: red, green, or blue. The strong force is what keeps the quarks bound together in groups of 2 or 3, forming protons and neutrons. Without the strong force, the nucleus of an atom would fall apart, and the universe as we know it would not exist. In short, the interaction between up and down quarks, mediated by gluons, is what creates the strong nuclear force, which holds the nucleus of an atom together. Understanding quarks isn't just about satisfying scientific curiosity. It's essential to understanding the very fabric of the universe. These tiny particles, despite their elusive nature, hold the key to unlocking the mysteries of matter and its fundamental structure. Each quark, with its unique set of properties, contributes to the complexity and diversity of the cosmos. It's through the study of quarks that we can explore the strong and weak nuclear forces, two of the 4 fundamental forces of nature. These forces govern the behavior of subatomic particles and thus the stability of atomic nuclei. Understanding these interactions gives us insight into the nature of matter itself. Moreover, the existence of quarks and their fractional electric charges challenge our traditional understanding of electricity, leading us to a more nuanced and refined comprehension. The heavier quarks, though less common, provide us with invaluable data when produced in high-energy particle collisions, further expanding our knowledge about the subatomic world. So, while quarks may be small, their impact on our understanding of the universe is colossal. They truly are the essential building blocks of matter.